Benjamin Asari Mafu is my name, a data science student of GCT. Today we are going to look at memory mapping and cache memory techniques. These are fundamental topics in computer architecture because they determine how efficiently a processor can access the data it needs. We will cover direct mapping, round-robin replacement, associative mapping, set associative mapping, and some general strategies for memory and cache. So let's think when it comes to the CPU, think about it as a fast worker, but then the main worker is like a storehouse far away. So let's say the CPU is in Accra and the main memory is in Tamale. So every time the worker needs something, it has to travel to Tamale, which will take a lot of time. So that's where the cache memory comes in as a smaller storehouse that sits right next to the worker. But the big question is, how do we decide where things go in the cache and how do we place them when the cache is full? That's what mapping and replacement techniques are all about. So let's move on to direct mapping. So in direct mapping, every block of main memory can only go into one specific cache location. Think of it like having a fixed locker number for each item. You always know where to find it. The memory address is split into three parts. We have the tag, which helps identify the block, and also we have the index, which tells us which cache line to look at, and the offset, which finds the exact word inside that line. This method is simple and cheap to implement, but it can lead to conflict messes if too frequently use blocks mapped to the same line. So um, that's a theory. Let me give you a practical example. Imagine we have 8 cache lines. Memory block number Memory block number 5 will go into line number 5%8, which is line 5. If another block, say block 13, also mapped to line 5, it will replace block 5, even if block 5 was still useful. That's the main weakness of direct mapping. Simplicity comes at a cost of flexibility. Yeah. So let's look at round robin replacement. Round robin is not a mapping technique, but it's a replacement policy. It tells us which block to remove when we need to make space. It's like taking turns in a game. We keep a pointer to the next slot to replace, and after each miss, we move to the next slot in a fixed order. It's predictable and hardware friendly, but not always optimal for performance. So let's look at a practical example. In a four-way set associative cache, the round robin policy would go through way 0, then way 1, then way 2, and so on, looping back when it reaches the end. So the ARM processor often use this because it's simple and deterministic, great for embedded systems where predictability matters. Now let's move on to fully associative mapping. So fully associative mapping is the most flexible option. Any block from main memory can go into cache line. This completely removes conflict messes because you are not restricted to a single slot. The downside is the complexity. The system has to check every cache line to see if the block is there, which requires expensive hardware called a content addressable memory. Yeah. So now let's move on to set associative mapping. Set associative mapping is like the middle ground between direct and fully associative. Like it's in the middle. The cache is divided into two sets. Like when I say it's in the middle, let's see. You see, when you buy a burger, you have bread down, then meat in the middle before another bread on top of it. So let's say the set associative mapping is the meat in it. Yeah. So this cache is divided into sets, and each set contains multiple lines. A block a block maps to exactly one set, but it can be placed in any of the lines within the set. This greatly reduces conflicts compared to direct mapping, but with less hardware complexity than fully associative caches. Most modern CPUs use this method. For example, a four-way set associative cache means each set has four possible slots. Yeah. So now let's move on to general memory mapping techniques. So cache caches also need policies for writes, whether to update the memory immediately or only when the cache line is replaced. We have replacement policies like least recently used or round robin, allocation policies for write misses, and even multi-level caches where we have L1, L2, L3 caches in a hierarchy. Advanced systems also use prefetching and coherence protocols to boost performance in multiple core systems. So to wrap up, each mapping and replacement technique has trade-offs between speed, complexity, and heat rate. Direct mapping is fast and cheap, but inflexible. Fully associative is flexible but expensive. Yes. So set associative gives us the best balance, and round robin is a simple, predictable replacement method. In a real world CPU designs, these techniques are useful to match the processor's performance, goals, and cost constraints. If you want, if you want more um, idea about this thing, you can visit www.khanacademy.com to get more of a idea about it. Thank you.